Hello, everyone, and thanks for joining us tonight. Um, I'm a physical oceanographer, so I care about the physics of the ocean, how it moves around, and how heat and salt transported around in the ocean. And on this map here, well, the first thing we have here is the sun, but it's just appropriately a nice yellow ball. And the role of the sun is to power the planet Earth. And I think I want to bring up on this first slide is uh, the picture of the blue planet. You know, it's the blue marble floating in space. And this is, of course, a satellite image taken from far out in space. But what you notice about it is that the Earth is mostly blue ocean. We know that the ocean covers over 70% of the Earth's surface. And the characteristic dark blue color of the ocean means that the sunshine that hits the Earth is mostly absorbed in the ocean. Now, this picture, there are some white clouds, and those white clouds are pretty good at reflecting light from the sun back into space. And of course, so is snow at high latitudes. But that dark blue ocean is very good at absorbing all the heat from the sun. And the other fact, well, a couple of facts about the ocean have much more heat capacity than the atmosphere. Uh, the water molecule is just about 800 times denser than the atmospheric weight of the atmosphere, and so the heat capacity is over 1,000 times larger for the bulk of the ocean compared to our thin light atmosphere. So that means that the ocean has the memory of the climate system. It stores all that heat from the sun and parcels it back out to the atmosphere, give us the climate that we observe. Also, of course, we know that the oceans have 97% of the free water on the planet. And of course, that's vitally important to the water cycle. And one of the points I like to emphasize is that the water cycle is mostly an oceanic and atmospheric phenomenon. And the land plays relatively a minor role, so of course it's very important to us. Let me move on to the water cycle. Well, no, I want to talk a little more about heat. We'll go up to the temperature ball here. And we just look at this picture of the annual seawater temperature at the surface. Reds, of course, are very high temperatures. These are temperatures in degrees centigrade. So 30 degrees is over 80 degrees Fahrenheit. And you see the tropics are warm and the high latitudes are cold. And of course, that has a great consequence for the ocean because the temperature of water tells us a lot about how dense it is. We know that cold water is denser than warm water. So what we have is this warm water in the tropics that's actually floating on cold water that's flowed underneath from high latitudes. And just to give you a little feel for how that varies with the seasons, here's monthly averages temperatures, surface temperatures plotted on the globe as the globe rotates, and you can see the migration of the warm water with the sun. So in the northern hemisphere summer, the warm water goes north, and in southern hemisphere summer, the warm water goes south. Just to give you a feel for how the climatic forcing, the seasonal forcing of the ocean surface temperature is occurring. Let me go now to this slide which shows a vertical profile of temperature in the ocean. So it's warm near the surface. It has a region down maybe to about 1,000 meters, depending on where you are, where the temperature drops pretty steeply. We call that the thermocline. Cline meaning rapid change. And then a deep the deep ocean is relatively uniform in temperature and mostly less than 4 degrees centigrade, less than about 40 degrees Fahrenheit. So that's the kind of picture that develops because, as I mentioned earlier, that cold water flows down from the high latitudes and sits underneath this warm water at the surface. And again, it's because of that density difference. Heat makes the water expand, cold makes it contract. So we're putting all this heat into the ocean from the sun's radiation. And the important thing that we'll be concerned with today is how that fuels the global water cycle. And let me start off with one of the movies here. And this is just a fairly simple, straightforward explanation of the water cycle. It's a very traditional picture. We see the sun providing energy to the earth. And a lot of that energy, of course, is going into warming the ocean. That causes the water to evaporate. And then it gets transported, in this case, over land and even up into the mountains where it's going to snow. But this whole cycle of precipitation contributing to here, we're showing groundwater transport as the snow melts and enters the system. Here we're showing runoff as the water flows into rivers and goes back to the ocean. And so that whole cycle of evaporating from the ocean, transporting onto land, and raining out or snowing out, and flowing back into the ocean is what's traditionally called the water cycle. But I have a problem with this picture as an oceanographer, and the problem really comes up from that view of the globe we saw. There's just a little bitty ocean here, just this small chunk of ocean, when in fact we know that the planet is mostly ocean. In fact, there was that quote that I didn't mention at the time, but Arthur C. Clarke said, we should have called this planet Ocean instead of Earth. Now, if we can look at some of the slides. This one is rather quantitative, but it shows the global reservoirs and fluxes. These reservoirs are thousands of cubic kilometers of water, and so there's a huge number here. Let's just do percentages. 97% of the water on the planet is in the ocean. Only 0.001% is in the atmosphere, and about 3% is tied up on land, mostly in the Greenland and Antarctic ice caps. And then the other numbers, the arrows here, show the flows between these reservoirs. And the largest one is evaporation from the surface of the ocean. It's a number we oceanographers like to use. It's called a Sverdrup, named for a famous oceanographer from Scripps. And so 13.5 Sverdrups of water evaporating from the surface of the ocean. A Sverdrup is a million cubic meters per second. It's let's see, it's the flow of the Amazon River, which is the world's largest river, amounts to 0.2 of a Sverdrup. The flow of all rivers over the whole globe only amounts to 1.3 Sverdrups. The flow of the Gulf Stream in the Straits of Florida is about 30 Sverdrups. So it's a big number, but it's the number that we have to use in oceanography to measure currents. Like I mentioned, the Gulf Stream is 30 Sverdrups, and further downstream it builds up to about 100 Sverdrups. You get similar numbers in the Antarctic Circumpolar Current and Kuroshio in the Pacific. So of the 13 Sverdrups evaporating from the ocean, about 12 are raining right back down on the ocean. And so what's left for land, and on land, of course, you have evapotranspiration. The land has its own small water cycle. But you see the flow of all the rivers is only about 10% of the evaporation from the surface of the ocean. So the oceans really dominate the global water cycle. if we go and sum up all our estimates of atmospheric transport and ocean evaporation precipitation, we can make a figure like this, which shows the north-south transports of water on the planet by the atmosphere in the dashed line and by the ocean in the solid line. And these are rough numbers. There are lots of things we don't know about the exact numbers yet. And that's why we're putting up all these satellites and sensors. But I just want to point out that the flow of rivers, such as here's the Mississippi, which is a large north-south river, makes a very small contribution when viewed in terms of the global water cycle. And let's go on then to the next feature here. We're going to talk about evaporation precipitation and get into more details about the water cycle. Of course, we know that water evaporates because a lot more when it gets warm. And here's a little pot of boiling water. It evaporates quickly when it's heated. And of course, get hot enough, it will turn directly into steam. And one of the important points is that as the climate warms, we're going to get more evaporation, and thus we'll expect an intensification of the water cycle. And that's a very controversial and important topic that we think we have a lot to say about with our measurements of salinity in the ocean. But let's take a look at the patterns of evaporation with the day-night cycle. This is just a fairly few number of days, but you can see that on land, most of the evaporation is occurring in the heat of the day. But over the ocean, the evaporation, which is the light blue color here, is more constant. It doesn't have that strong day-night cycle. It just depends more on the strength of the winds during the storms. You can see this is a large storm in the Atlantic, and the evaporation stayed pretty steady, independent of the day-night cycle. And then just to take a look at how precipitation varies, this is just a monthly distribution of precipitation. The dominant feature you see, the prominent rain bands in the tropics, and how they shift north and south with the seasons. Again, following the sun the way the warming did. So we call it the intertropical convergence zone here in the Pacific, where a lot of rainfall falls, and that migrates north in the summer, south in the winter. If we develop maps of the global evaporation in the top here and the global precipitation in the bottom, now these are averages that we developed over about 20 years, from about late 1980s into the 2000s. We've developed a map of the evaporation here in the upper panel. You see a lot of it occurs in mid-latitudes, not so much on the equator, but a fair bit, several meters per year in mid-latitudes and in these warm currents adjacent to continents, such as the Gulf Stream here in the Atlantic and the Kuroshio here in the Pacific. And we already saw some of the patterns of precipitation, the concentration of precipitation in the tropics under the intertropical convergence zone. And there's also a fair bit of precipitation at high latitudes, and certainly associated with what we call western boundary currents, the Gulf Stream in the Atlantic and the Kuroshio in the Pacific. So what we've done recently is combine these maps of evaporation and precipitation and taken the difference to get the net flow of water from the surface of the ocean. And here you see that The mid-latitudes are where the water originates, where the water is leaving the ocean in the net. And the tropics, the ITCZ, the blue regions are where the water is entering the ocean as rainfall. And at high latitudes, we know it rains a lot in the British Isles, keeps Ireland green. We know it rains a lot in Seattle. So high latitudes get the rain, low latitudes get the rain, and mid latitudes are the source of the water that is raining out in other places. That's where most of the evaporation occurs. And on land, that's where the deserts are. This is the Sahara Desert would be at the same latitudes of the evaporation region. So if an oceanographer looks at that picture of evaporation precipitation, he can come up with what I call the oceanographer's global water cycle that I think more appropriately has a large ocean and just a little bit of land here in the corner. So what we're looking at is evaporation from the surface of the ocean in mid-latitudes, and then it's feeding just about equally to precipitation in high latitudes and precipitation near the equator. So those, I have these arrows in the atmosphere, but note that I also put arrows in the ocean. And we're talking about meters per year of evaporation and precipitation. And of course, that would cause sea level to fall or rise regionally. And that doesn't happen. So what has to happen is the water flows in the ocean from those high rainfall regions and feeds into the evaporation regions at mid-latitudes. Otherwise, we'd have these variations in sea level. So this is the oceanographer's water cycle, and I use it to tease the meteorological community because they tend to be very focused on what's going on land. So we've seen the patterns of evaporation and precipitation, and the effect that we're interested in is how that's going to change the sea surface salinity. Of course, here's a very simple diagram. We know that when you add water to the ocean, you're going to dilute it. You're going to dilute the salt concentration. Precipitation will certainly do that. River runoff will do that, and so will the melting of ice. And of course, the flow of groundwaters into the ocean. On the other side, the things that increase salinity, of course, are mainly the evaporation of seawater. That's how colonial people on Cape Cod made salt in the old days. They used windmills to pump water up into evaporation pans and let the sun do its work so they could make salt. And another process that's probably less well known, when seawater freezes at high latitudes, the water freezes out without the salt and tends to let the salt drain out of the ice. And so sea ice that's been formed, especially after several years, becomes nearly fresh with no salt in it. Now, the average salinity content of the ocean is not all that high. It's only 3.5%. Of course, that's quite a shocking taste when you take a swim in the ocean and you get a little in your mouth. But you know, it's a modest amount, I guess, 3.5%. And when we look at different map of the evaporation precipitation, this is different units here, millimeters per day. Again, we see the high evaporation regions at mid-latitudes, the high precipitation regions in the tropics and high latitudes. And then we'll look at the pattern of surface salinity around the global ocean. And we see that those high evaporation regions in mid-latitudes are the saltiest parts of the ocean. of the open ocean. Here, instead of 3.5%, it's 3.7%. And then high latitudes, it'll get down to 32 parts per thousand, or even 30 parts per thousand up in the Arctic. And those kinds of variations are obvious. We also see a very strong difference between the Atlantic Ocean and the Pacific Ocean. The Atlantic is quite a bit saltier than the other oceans. And that has very important consequences for ocean circulation, which we'll talk about shortly. And to make this comparison a little more close up, for the plotted the North Atlantic here, and evaporation and minus precipitation is on the left, and the sea surface salinity distribution is on the right. We've also used proper color images of the continents here, and what intrigued me about this picture, when we made this map of evaporation minus precipitation, you can see the transition here where it's a net of 0, which is just exactly the same place in the Atlantic, just off the coast where Africa transitions from green to brown. So here you have tropical rainforest, and then savanna, and you're transitioning to the Sahara Desert. This transition region is called the Sahel. And but it was quite striking that it corresponds very precisely with the distribution of evaporation and precipitation over the ocean. So some people like to pretend that what's going on over the ocean doesn't reflect what's happening on land, and I use this figure to dispute that. So this big patch of very salty water out here in the middle of the Atlantic was of special interest to us. This is where evaporation is large, and ocean currents conspire to push the salty water into this one place. And the SPURS experiment that you're hearing about both in Eric's talk last week, and you'll hear more from Fred next week, is designed to go out and try to understand how the ocean is making this very salty water. And here's some very old maps. People like to talk about the river of salt, and the upper map shows the distribution of salinity, of the highest salinity over the upper several hundred meters. And you see there's the high salinity at the surface in this region, but it becomes a subsurface salinity maximum as you go down to the southwest. And if we go along this line here, in the lower panel, we see what we plotted is the salinity anomaly, the deviation of the salinity from some average value. And so from the latitude of where we did the SPURS experiment out here, we see this salty water being carried subsurface in the ocean. Very interesting process. And I've spent a lot of my career looking at how this river of salt mixes with the water underneath it in the region of South America here. So if we look at the vertical profile, this is just a generic vertical profile, actually more from the Pacific than the Atlantic, but it's salty at the surface and fresher at depth, and that fresh water has flowed in from Antarctica. That makes for an interesting situation. Now we know that adding salt to water makes it denser, and if you decrease the salinity by freshening, you make the water lighter. So how can that be? We've got heavy water on top of light water. Well, we saw the answer to that earlier on with the temperature profile, because the temperature goes from warm near the surface to cold at depth. So the temperature stabilizes the vertical density stratification of the ocean in the tropics and subtropics. In other places, up in high latitudes where we have rainfall at the surface, the halicline is reversed. We have a low salinity near the surface and saltier water at depth. And the temperature profile can be either way. It can be cold near the surface and warm at depth. In this case, the salinity is dominating the density profile. So the key message is that these changes in temperature and salinity have very important consequences for the density of seawater. And if I just finish up with this section, one more map of evaporation minus precipitation and at the top, and one more map of the salinity at the bottom for the globe, side by side. Again, we see this contrast between the Atlantic, the salty Atlantic, and the relatively fresh Pacific, especially the North Pacific. And one of the interesting puzzles about the planet Earth is why the Atlantic is saltier than the Pacific. And we think it's largely because there is little in the way to block the transport of water evaporated from the surface of the Atlantic in the trade winds. There's nothing to block it from going into the Pacific, whereas water evaporated in the Pacific may end up in the Indian Ocean, and water evaporated in the Indian Ocean is going to get blocked by Africa. But the narrowness of Central America and the Isthmus of Panama really allows a lot of water vapor, water evaporated from the surface of the Atlantic under the trade winds to be carried into the tropical Pacific where it falls out as rain. So there's this sort of hemispherical water cycle going on, not north-south like I showed before, but from east to west, whereas water is exported from the Atlantic into the Pacific. And as a consequence, the Pacific, being fresher, it ends up being about 50 centimeters higher than the Atlantic in its sea level. And that water ends up flowing through the Bering Straits and comes back into the Atlantic that way. So the water cycle has this big component of the atmospheric transport from Atlantic to Pacific, and then a return flow through Bering Straits and through the Arctic to return that water to the Atlantic. So, moving on to density, which we know is controlled by temperature and salinity. And this is just a typical diagram for the subtropics, warm surface waters, a thermocline, where the temperature drops off. And if we look at density, these are densities in grams per cubic centimeter. See this change. And so this thermocline is strongly stratified, and that stratification tends to inhibit the mixing rate. That is, the only way you can get mixing in this region is if the internal waves that are there will break. And you probably all know what internal waves are, and maybe we'll have a little demonstration here shortly. Again, I mentioned the deep water is rather uniformly cool, and this region of strong stratification is basically hard to mix. Now, I want to flip over to one of the films here, and these are just some little movies that students have made, and I don't think we'll have the soundtrack, but he's got light water on the right side and denser water on the left, and they just pulled out a barrier, and you can see how the dense wants to flow under the lighter, and you can just change the density by adding salt and make it more dense. And you can see the internal waves sloshing back and forth in that little demonstration. So that's the kind of simple thing that you can do in a classroom. And that kind of distribution of densities is really important to the ocean circulation. We saw those pictures of how the tropics were warm and the high latitudes were cold. And what that does is give you a warm upper ocean and then a cold deep ocean. Great. I want to go now to the talk about how density drives the ocean circulation. And I think we'll start here with one of the movies. There are other movies here which you can take a look at your leisure. This is a map of currents in the North Atlantic Ocean, and the red currents are warm surface currents, and the blue arrows represent cold deep currents. And what you'll notice here in a few regions here in the Labrador Sea, we're looking over the Straits of Gibraltar towards Labrador. The red arrows are converting to blue, and they're sinking. And the Labrador Sea is one of the regions where heat is lost to the atmosphere and dense water is formed. And also up in the Norwegian Greenland seas, you see red arrows going into those seas and blue arrows coming out. This we call the thermohaline circulation, and it's very important. It's stronger in the Atlantic than the Pacific because the Atlantic is so salty. It's easy to cool off that salty water and make it denser than anything around, and so it's going to form. And here's just the general schematic for the whole globe. Again, the red arrows represent warm surface waters, and the blue arrows represent cold deep waters. And so these deep water formation regions in the Labrador Sea and Norwegian Greenland seas are important places. And one of the reasons we have such an interest in the salinity of those waters is because if they got too fresh, they would inhibit the overturning of the thermohaline circulation. That is, they could actually shut it down. And this seems to have happened in the past when in the decay of the last ice age, 20,000 years ago, it was at a peak. But then the Earth's orbit changed slightly, and there was more sunshine in the northern hemisphere summer that was melting the ice, and a large lake of melt water formed in Canada, and it seems to have flooded out in one great pulse when an ice dam broke, and it caused a big disruption to the ocean circulation and prevented the dense water, the water from getting dense enough by cooling because it was so fresh. So both heat and salt are very important to the ocean circulation. And when we get too much freshness at high latitudes, it might shut off the thermohaline circulation. We know that it has done that in the past. And there's been some concern that as we melt Greenland's ice cap, we could have that happen again in the future. I personally don't think so. I think it's happening much too slowly to have that kind of dramatic effect. But we do see changes in salinity, and that'll be the next topic here. And here's the sort of first introduction to it. We've taken this section along this black line through the Atlantic here. It's kind of convoluted, follows the continents to some extent. So it's a vertical section from the surface down to 6,000 meters, and it goes from 60 south in the Falkland Islands on the left, all the way up to 80 north in Greenland, Denmark Strait, and Greenland Sea. And what we've plotted is the change in salinity from the 1990s compared to the 1960s. So over that 30-year period, we found that in mid-latitudes and near the equator, the water has gotten saltier, gotten redder, and at high latitudes, where the water is already fresh, the water has gotten even fresher. And you can see it's penetrating down into the intermediate and deep circulation at high latitudes. So those changes in salinity are something that oceanographers have been documenting for years, and we're starting to get concerned about it. And we've made some progress with new observing tools on how that is impacting the global water cycle. So just to sort of look at the big picture here, we know that the Earth is warming. These are show the temperature changes from probably about 1850s to 2005 or so. And these are carefully constructed from temperatures on land and on the ocean. And the dots represent the annual average, and then the red line represents the 5-year average. And it's been especially strong since about the 70s. We're in a period of pretty strong warming, about half a degree centigrade since the 70s. And the important thing for us is that we expect that to have a consequence of really intensifying the global water cycle. And this plot shows the vapor pressure of water as a function of temperature. Now, this is just derived from the thermodynamic properties of the water molecule. It's dictated by the physics of the water molecule. The important thing to note is that the average temperature of the globe right now, the average surface temperature of the planet is around 15 degrees C. And at that temperature, the rate of increase is about 7% increase in vapor pressure per degree C. And you'll notice this curve is not a straight line, it's an exponential curve. And the fact that you could get a 7% increase for a 1 degree change suggests that we could be in for a wild ride in the climate system in future. You can see that as temperatures get just a little bit warmer, we can hold a lot more water vapor in the atmosphere. That will intensify the water cycle. Now, this is a point of some controversy in models. The meteorologists believe that there are certain feedbacks in the climate system in the atmosphere that cause the reaction of the intensification of the water cycle to be less than this 7% per degree. They think it's only about 2% per degree. But if we look at the oceanographic data, which I think is a better indicator of the water cycle, we come to a different conclusion. And this comes from looking at the changes in salinity over the global ocean. And again, here's another map of the global ocean salinity. And again, the salty Atlantic is redder, the Pacific is bluer. If you look at the change in salinity over 50 years, and going back 50 years, our data weren't so complete, but for the last decade or so, we've got really quite good data on ocean salinity. And what we're seeing are some remarkably strong trends. The salty areas are getting saltier, and the fresh areas are getting fresher. And this is a change of 0.2 in salinity. So those are pretty large changes for an oceanographer. And that change over the 50 years is in pretty good agreement with that basic idea of intensification of the water cycle corresponding to 7% per degree. And it's in not such good agreement with the meteorologist's claim that it's only going to be about 2% per degree. Now I've got another slide showing that. Here's the sea surface salinity in the top panel, the change in salinity over the 50 years. Again, the red areas are getting redder and the blue areas are getting bluer. And then here's the distribution of evaporation and precipitation. My main point is most of the water cycle is over the ocean. And when we look at ocean salinities, which are a direct indicator of the intensity of the water cycle, we see a strong intensification of salinity contrast, which has to be tied to a rapidly strengthening global water cycle. There are lots of consequences for that. When you put water vapor into the atmosphere, you provide energy to storms. And we've certainly seen a lot of intense storms this past winter. And in my part of New England, we're anticipating another one in the next couple of days. What we think is going on is when you have that much more water vapor available, it provides fuel to the storms. When the water vapor in the atmosphere condenses into rainfall, and the rain falls out, it releases heat to the atmosphere, and that heat drives strong convective motions in the atmosphere. And so intensification of storms is one of the consequences of an intensifying water cycle. And this plot shows that we seem to be getting more of these short duration storms. Now, I just want to conclude with one word slide, if you'll forgive me. What we're seeing in the ocean indicates that significant changes are underway in the global water cycle. And I'd like to emphasize it's primarily an ocean atmosphere phenomenon. We see the high salinity regions are getting saltier, the low salinity regions are getting fresher, and I claim that it represents the very best evidence we have for strong intensification of the global water cycle. Now, in these 3 lectures, you'll be hearing a lot more about our study called SPRS, Salinity Processes Upper Ocean Regional Study, which we're focusing on the high salinity region of the North Atlantic. We had our first cruise to that region back in September, and I'm going out for another cruise to that region a little over a week from now. And what we discovered in September, we went out to this place where the salinities have always been high in the open ocean, and we found that they were higher than had ever been observed before. That really reinforces the trends that others have documented about how salinities are changing. And here, we went out looking for the high salinity region in the North Atlantic, and we found it was much saltier than we had ever seen before. And to me, that's very shocking and kind of alarming. We could be in for a pretty wild ride in the weather if we see the water cycle intensifying as strongly as we seem to be seeing the ocean salinity contrast intensifying. So, well, I hope you all gathered some good science from this discussion, and I am available to answer any questions